We have studied about the maximum preparation methods of alkanes. One more is left, which is the preparation of alkanes from carbonyls, that is aldehydes and ketones. After that, we will move to the physical and chemical properties of the alkanes. So, let us start with preparation of alkanes from carbonyl groups. Okay. Mostly aldehydes and ketones. Okay. So, what are aldehydes? Aldehydes are like this and ketones are like this. Okay. So, in aldehydes, this is the carbonyl carbon. It is bonded to one carbon in an alkyl group and double bonded to oxygen and bonded to another hydrogen atom. But for ketones, it is bonded in two sides with two different or same alkyl groups and double bond O. Okay. So, the first one is Clemenson's reduction. Clemenson's reduction. In this method, aldehydes or ketones in presence of zinc amalgam, that is zinc mercury, and concentrated HCl, that is hydrochloric acid, gives alkanes. Okay. So, the reagent for Clemenson reduction is zinc amalgam and concentrated hydrochloric acid. So, let us say we have this. It is treated with zinc amalgam and HCl. What it will give? There are two carbons, right? So, it will give ethane. Now, let us say we have this ketone. In presence of zinc amalgam and HCl, it will give this alkane, right. So, this is the Clemenson's reduction. Now, one limitation of this Clemenson's reduction is it is not used for acid sensitive groups. Because this reaction takes place in an acidic medium. So, if in the reactant there are some other acid sensitive groups, for example OH, okay, that is the alcohol group, then they can have some side reaction with these reagents. So, this reaction is not applicable for acid sensitive groups. The second reaction is Wolff-Kishner reduction. Wolff-Kishner reduction. So, Clemenson reduction was carried out in acidic medium. Okay. Wolff-Kishner reduction is carried out in basic medium. In this case, the reagent is NH2NH2, that is hydrazine, and potassium hydroxide. Okay. So, this is basic medium. So, aldehydes or ketones in presence of hydrazine and potassium hydroxide will give alkanes. So, let us say acetone. It is treated with hydrazine and potassium hydroxide. Then it will give propane. Okay. Now, one more example of the Wolff-Kishner reduction. If this is an aldehyde and it is treated with hydrazine and potassium hydroxide, then it gives this alkane. We have completed the methods of preparation of alkanes from other types of compounds. Now we will discuss about the physical properties of alkanes. Okay. So, alkanes are the hydrocarbons and they can have different types of physical properties. So, the first one, the most important thing is alkanes are very less reactive, and the lower alkanes like from methane to butane, they are gaseous, and the higher alkanes can be liquid or solid. So, we will see the physical properties of alkanes. Okay. So, the first thing is alkanes are almost non-polar. Okay. Why non-polar? Because alkanes are made up of carbon-carbon and carbon-hydrogen bond. So, carbon-carbon and carbon-hydrogen bonds are covalent bonds, right? And also the electronegativity difference between carbon and hydrogen is very low. Due to these reasons, alkanes are mostly non-polar. The second feature is alkanes possess weak van der Waals forces. Okay. What are van der Waals forces? It is non-covalent interactions. Okay. Now, higher alkanes will have more van der Waals interactions. Okay. So, the more the van der Waals interaction, the phases will also change. So, gases have lowest van der Waals interaction. So, from C1 to C4, that is methane to butane, that is methane, ethane, propane and butane, they are gases. Okay. Gases at room temperature, that is around 298 Kelvin. 298 Kelvin means 25 degree Celsius. So, at room temperature these four are gases. Now, from pentane, that is C5 to C17, these are liquids. And C18 onwards, that is C18 and the higher alkanes, they are solids. Okay. So, these change in phases is due to the van der Waals interactions. The next feature of alkanes are that they are colorless and odorless. And the next feature is due to non-polar nature of alkanes, they are insoluble in water. Okay. What do we know? We know that like dissolves like. So, by this concept of like dissolves like, we know that polar solvents dissolve polar compounds and non-polar solvents dissolve non-polar compounds, right? Water is a polar solvent. So, water dissolves mostly polar compounds like the salts and acids. So, alkanes are non-polar in nature. So, they cannot be dissolved in water. They can be dissolved in organic solvents. This is the reason why when we have some grease stains on clothes, for example. What are grease? Grease are the mixture of higher alkanes. Now, to remove a grease stain, washing with water is not sufficient because water cannot remove grease stains. For that, we need to use some solvents which are taken out from the fraction of petroleum, or the petrol based solvents are used for the removal of grease due to this non-polarity of alkanes. The next feature is with increase in molecular weight, boiling point of alkanes also increase. Okay. Why this is like this? If molecular weight increases, that will mean molecular size will also increase. Okay. When molecular size increases, surface coverage will increase, which will mean greater van der Waals forces. So, greater van der Waals forces will mean high boiling points. See, what we had discussed, that the lower alkanes are gases. That means in the lower alkanes their molecular weight was also very less and their size was also very less. So, they had low van der Waals forces, due to which their boiling points are so low that they exist already in the gaseous form at room temperature. Then C5 to C17, these had some intermediate size. So, they had more van der Waals forces than these lower alkanes. So, they exist as liquids in room temperature. And the higher alkanes, they have so much molecular weight and they have so high van der Waals forces that in the room temperature they exist as solid. So, of course, if we compare the boiling points, that is already liquid, they will have a lower boiling point as compared to the solids. So, this property is explained. Now, according to the boiling point, there is one more discussion. Let us say one is butane and one is isobutane. Okay. So, they have same molecular formula. So, they have same number of carbons and hydrogen, but do they have same boiling points? The answer is no. Since they are two different compounds, their boiling points are also different. Why? Because the branched chain molecules acquired a sphere-like shape. Like if we compare, then this is nowhere spherical, right? But for this compound we can consider it like this. So, branched chain, that is more the number of branches, it acquires a more spherical shape. For example, let us say if we compared the isomers of pentane, okay, and let us say it was something like this, and imagine the straight chain pentane. So, this has a spherical kind of shape. So, when there is spherical kind of shape, so the area of contact becomes smaller area of contact. So, low van der Waals forces, therefore lower boiling point. But for the straight chain compounds, higher area of contact. So, they will have more van der Waals forces and more boiling point. So, straight chain will have higher boiling point than branched compounds. Okay. These were the major physical properties of the alkanes. In the next lecture, we will study about the chemical properties of the alkanes or the reactions of alkanes. Thank you.